Hey there everyone, welcome to Bright Engineering. Today we are going to continue with the circuit analysis and we are going to look at the Thevenin's theorem, right? So we are being asked to find I, which is the current flowing through this 1 ohm resistor, right? So when we are considering Thevenin's theorem, the first thing that we have to do is to find the Thevenin resistance, and after that we have to find the Thevenin equivalent voltage, and then we'll be able to find the current that is flowing through this 1 ohm resistor, right? So when you are considering Thevenin, the first thing that you have to do is always omit the resistor to which you are finding the current that flows through, right? So it means that with this particular 1 ohm resistor, we are going to assume that here is an open circuit, so we are going to omit this whole thing from the diagram, right? Don't worry, at the end of the day we will bring it back and then you see what we mean. Once you omit this, then every voltage source in the circuit now becomes a closed circuit and every current source now becomes an open circuit, right? So when you have to draw an equivalent diagram for that, this is what we are going to get. Right, so we've opened this side to eliminate the 1 ohms. We've now open circuited the current that is flowing through this branch, and now we've closed circuited the voltage that is also through this branch, right? So now we are left with these 3 resistors, right? So now what we have to do is to find equivalent resistance, and here the equivalent resistance is what we call the Thevenin resistance, right, which can be represented by RT. Right? So when we open this side, now we look at the diagram from this angle. So it means that we have to now calculate the equivalent resistance from behind it, right? And then since this branch is open circuited, it means that when current is flowing through these 6 ohms, that same amount of current will flow through this 6 ohms. Because of this open circuit, none of them will pass through this branch, right? So it means that this and this are in series, and if they are in series, then the equivalence of that is going to be 6 plus 6. But then the total of these 2 is in parallel with this 4, right? Because they are sharing these 2 common nodes, right? So this 2 is going to be in parallel with the 4, right? So we are going to get 12 times 4 divided by 12 plus 4, right? So now our answer is going to give us 3 ohms when you punch it into your calculator, right? So now we can write our RTH somewhere here, 3 ohms. We'll use it, right? So once we are done with our RTH, now we have to find our Thevenin equivalent voltage, right? That's the voltage that is going to be across this particular resistor. And once we've short circuited this resistor, it's assumed that the voltage that is here at this particular node, right, that flows along this is the same thing that's going to flow along the 1 ohm, because we say that parallel voltages are the same, right? So once we're able to calculate this nodal voltage, it means that we have the voltage for the 1 ohm too as well, right? So this time around we draw our circuit with all the sources in there. Okay, so we have our 12 volts here, we have our 6 ohms, our 6 ohms, our 4 ohms, and now we have our 2 amps current, right? So we know that with this we have 2 nodes here. So this is going to be our V1 and this is going to be our VTH, because the voltage here is going to be our equivalent voltage, right? All right. So with this nodal voltage, now we can apply our nodal analysis to this one, right? So we know that when we have a nodal voltage here, we are going to get at node 1, we are going to get 12 minus V1, because this current source, this voltage source will produce a current going this way, right? And now we have to assume that all other currents are leaving the node, so this will be leaving this node. But then interestingly, we have a current that is already flowing into the node, so we leave it just like that, right? So I'm going to get 12 minus V1 over 6 plus this current, which is the 2, which is equal to this V1 minus VTH divided by 6, right? So now we can write an equivalent, we can just multiply through by the LCM. So we are going to get 12 minus V1 plus 12 is equal to V1 minus VTH, right? So with this, we can now make V1 stand alone. So we are going to get 2V1 is equal to 24 plus VTH. And now V1 is equal to 24 plus VTH on 2, right? So now we have the value for V1. And then at node 2, which is this side, already this is flowing into this node, right? So we are going to get V1 minus VTH over 6, and it's equal to, because we are going to also assume that this is leaving, right? And this is going to be equal to VTH minus the reference node, which is going to give us 0, and then we can choose to just write VTH, right, divided by 4, right? And the LCM of this is going to give us 12, so we can just cross multiply. And 12, 6 goes into 12 2 times, so you are going to get 2V1 minus 2VTH, right, is equal to, here we can see that 4 goes into 12 3 times, so 3 VTH, right? When this crosses and come here, we are going to get 5 VTH. So 5 VTH is equal to 2V1. So VTH is 2 on 5 times V1, right? And we already know our value for V1 here, so we can just substitute it in this, right? So if you are to substitute this one, this is 2, right? So if we are to put equation 1 into, equation 1 into 2, then it means that we are going to get VTH is equal to 2 on 5 into bracket our V1, which is 24 plus VTH all over 2, right? And multiplying this, we are going to get VTH is equal to 48 plus 2 VTH divided by 10, right? We cross multiply this to get 10 VTH is equal to 48 plus 2 VTH. Now we can subtract this from this to get 8 VTH, and then it's going to give us 48. So dividing both sides by 8, now our VTH is going to be equal to 6, right? And then don't forget, this is 6 volts, right? So now we have RTH to be 3 ohms, and we have VTH to be 6 volts, right? But then mind you, when we were solving this particular question, we open circuited the currents that the resistance that the current is supposed to flow through, right? And then we didn't use it. So whenever you are using Thevenin's theorem, after you are done finding your RTH and your VTH, you have to draw an equivalent circuit for it, right? And the equivalent circuit has to contain your VTH and then your RTH and then the load resistance, the one that you omitted, right? So that then now you can find the current that is flowing through this, right? And we know that our VTH is 6, our RTH is 3, and then the RL, the load resistance, or the resistor that the current was supposed to flow through, was 1 ohm, right? So now we can gladly find the current, and because these two are in series, it means that the same amount of current is going to flow through both of them, right? So to find the current flowing through, we know that I is equal to V on R from Ohm's law, right? So current is going to be the VTH that we have here, which is the 6 volts divided by our R, and here our total R is this, the RTH plus this RL, right? So it's just RTH plus RL, which is going to give us 6 over 3 plus 1, which is 6 divided by 4, and now our answer is 1.5 amps, right? So thank you very much. If this video has been helpful, please don't forget to subscribe, share, comment, and like.